To know exactly how a heavy industrial induction motor will perform at full capacity, you could bolt it to a test bench and load it to its absolute physical limits. But in the real world of engineering, that approach has a hard ceiling. Pushing massive motors through their complete operational envelope on a dynamometer takes enormous amounts of power. It is expensive, highly impractical, and severely risks melting the very copper windings you are trying to measure. The engineering solution is a mathematical shortcut. Instead of mapping every single data point on a physical test bench, we extract the absolute boundaries of the motor using just two isolated, highly controlled tests, the no-load test and the blocked rotor test. These two sets of numbers look isolated, but they contain the exact electrical constants required to define the motor's complete operating envelope. This transformation shows the most efficient way to process those constants by translating them directly into geometry. This is the Heyland circle diagram. This single semicircular arc acts as a physical proxy for the machine. Any possible combination of slip, efficiency, and torque exists as a mathematically proven coordinate somewhere on this line. By projecting raw test bench data onto this specific geometric curve, we can calculate full load performance without a dynamometer. We can trace exactly how thermal resistance silently robs output torque, and prove mathematically why low-speed motors are geometrically constrained to poor power factors. Consider a standard industrial 50-horsepower, 440-volt induction motor. The mapping process starts by focusing on its blocked rotor test data, where the rotor is physically locked in place to measure the current extreme. If you apply the full 440 volts to a locked rotor, the resulting current spike will instantly destroy the windings. To safely capture this boundary condition, the test is restricted to exactly half the rated voltage, 220 volts. Under this 220-volt test, the locked stator pulls 202.5 amps, but this is an artificial safety limit, not the motor's actual electrical ceiling. Because the equivalent circuit behaves linearly when the rotor is locked, the safe test data can be multiplied outward to match the motor's full 440-volt operating environment. Doubling the test voltage doubles the current, giving us a scaled short-circuit current of 405 amps. This defines the absolute boundary limit, the maximum theoretical current that would flow if the motor were jammed at full power. With the scaled voltage, current, and wattage locked in, we divide them out to isolate the physical properties of the internal wiring. We extract total equivalent impedance, the internal resistance, and the leakage reactance. For this 50-horsepower machine, the calculation yields an equivalent impedance of 0.627 ohms, a resistance of 0.255 ohms, and a leakage reactance of 0.573 ohms. These three electrical values act as the motor's DNA. They provide the exact dimensional inputs required to draft our geometric map. We establish the foundation for our geometry using a Cartesian plane. We map the active, working current along the horizontal axis and the reactive, lagging current against the vertical axis. The first boundary condition plotted on this grid is the no-load magnetizing current. This is the baseline amperage required just to maintain the magnetic field and keep the empty rotor spinning, sitting close to the vertical axis. This coordinate system plots the second boundary condition directly alongside it. We stretch our newly scaled short-circuit current of 405 amps out into the grid, angled by its specific power factor. These two vectors act as the start and end anchors for the motor's performance curve. But the total spatial size of that curve is dictated entirely by one variable, the equivalent leakage reactance. The mathematical rule for drafting the circle's diameter is absolute. Divide the phase voltage by that leakage reactance. Applying that formula to this motor yields a geometric diameter of 443.3 amps. We strike an arc with this dimension perfectly through our anchor vectors. This establishes the governing law of the Heyland diagram. Every possible steady-state operating condition this motor will ever experience exists exclusively as a point along this single curve. Mapping the performance to this geometry solves complex engineering questions instantly, bypassing tedious circuit algebra. To locate the motor's maximum theoretical power factor, you simply draw a straight line from the origin until it rests perfectly tangent against the outer edge of the semicircle. The circle diagram transforms abstract electrical parameters into an immediate visual readout of the motor's absolute physical limits. However, the perfection of the geometry we just drew has a constraint. The baseline circle assumes the copper windings inside the motor remain at a cold, theoretical 25 degrees Celsius. Physical reality is harsher. Continuous industrial operation generates heavy internal heat, and as the copper temperature rises, its electrical resistance climbs with it. A second physical complication occurs at startup. High-frequency currents in the rotor force electrons toward the outer skin of the conductors. This skin effect pushes the effective AC resistance up to 1.5 times the baseline DC value. When we analyze thermal impacts on the equivalent circuit, we find that leakage reactance remains unaffected by temperature. Because that reactance does not change, the overall diameter and the outer boundary of the circle diagram remain permanently fixed. Heat cannot shrink the outer shell of the performance envelope. What it does change is the distribution of power along that curve. As internal resistance increases, the point of maximum torque is forced to slide further down the arc, altering performance at specific operating speeds. This chart demonstrates the penalty using the torque equation at a fixed 5% slip. The cold, 25-degree baseline outputs 264 Newton-meters of torque. But at an operating temperature of 75 degrees, that drops to 223. Factoring in the AC skin effect pulls the actual delivery down to just 178 Newton-meters. Failing to correct for operating temperature and skin effect will cause you to overestimate actual torque delivery by over 30%. Pure DC resistance values do not provide an accurate prediction of real-world industrial output. Beyond thermal constraints, the diagram exposes the mechanical design limits that dictate a motor's speed, the stator pole count. We analyze this by comparing 3 different motors running on the exact same voltage: a high-speed 4-pole motor, a medium-speed 8-pole motor, and a low-speed 12-pole motor. Physically lowering the synchronous speed of a motor requires packing more magnetic poles into the stator housing. This layout requires longer end winding paths and a larger total air gap volume inside the machine. That physical layout creates an electrical penalty. The extra wiring increases the motor's internal leakage reactance. This side-by-side layout shows the geometric result. Because the voltage is fixed, driving the leakage reactance up physically shrinks the total diameter of the performance circle. These low-speed, high-pole designs suffer a second consequence. Forcing magnetic flux across their larger internal air gaps requires significant amounts of magnetomotive force. Generating that force requires pulling a larger magnetizing current from the grid, a purely reactive current that performs zero physical work. These two effects compound geometrically. In low-speed motors, the reactive magnetizing vector stretches higher on the axis at the exact same moment the overall performance circle is shrinking. This warped ratio between magnetizing current and circle diameter significantly impacts efficiency. Because the origin point sits so high relative to the tiny circle, drawing a tangent line strikes the outer edge at a severely flattened angle. The poor power factor found in low-speed induction motors is an inescapable geometric consequence of magnetic design, perfectly visible in the Heyland diagram.